Trigonometry, the trig ratios for any size angles. Trigonometry with any angle. If we have a right-angled triangle, then the sine of theta is the opposite over the hypotenuse. But this definition only applies if theta lies between 0 and 90 degrees, because it's an angle in a right-angled triangle. So instead, let's consider a circle with radius 1. Now we can draw a line at an angle theta to the x-axis, and then we can draw the right-angled triangle OPQ. Now, the lengths OQ and PQ are the x and y coordinates of P. Now we notice the cosine of theta is the adjacent over the hypotenuse, which is OQ over OP, or x over 1, or just x. And the sine of theta is PQ over OP, which is equal to y over 1, or just y. So, if the length of the hypotenuse is 1, then the point P has coordinates xy, and cosine of theta is equal to x, sine of theta is equal to y, and tangent of theta is equal to y over x. In this case, theta is an angle measured anti-clockwise from the x-axis. If the angle is measured clockwise, then theta is negative. We can see this in the two diagrams. In the first diagram, theta is 120 degrees. In the second diagram, because we're going clockwise, the angle is minus 60 degrees. Now, since we can draw any angle and read off the coordinates of x and y, we can find the sine, the cosine, or the tangent of any angle. Now, it's worth noting, if we draw the tangent of the circle, AB, and extend the line OP to meet the tangent of the circle at B, then the tangent of theta is AB over AO. Now the length AO is 1, it's the radius of the circle, so the tangent of theta is AB over 1, or the tangent of theta is AB. So the tangent of the angle theta is equal to the length of the tangent AB. That is how the function tangent of an angle gets its name. Now let's look at the graphs of trigonometry functions. Now we can use a calculator to find the sine, cosine, or tangent of any angle. So we can create a table of values of sine, or cosine, or tangent, and plot the graphs of each. Here we're going to take the graph going from 0 degrees to 360 degrees. So if we start with y equals sine x, we can draw a table, fill in the angles. I'm going up in steps of 30 degrees, and we can get the sine of the angle using a calculator. This gives us the sine of the angle is 0, 0.5, 0.87, 1, 0.87, 0.5, 0, minus 0.5, minus 0.87, minus 1, minus 0.87, minus 0.5, 0. And if we draw a graph grid and plot these points, and then join with a smooth curve, we get a wave function. Similarly, if we draw the graph of y equals cos x, we can draw a table, choose values of x from 0 to 360 in steps of 30, and then fill in the values of cos x. And they are 1, 0.87, 0.5, 0, minus 0.5, minus 0.87, minus 1, minus 0.87, minus 0.5, 0, 0.5, 0.87, and 1. We can plot those points on a grid, and join with a smooth curve. Again, we have a wave function. Now, we can make up a table for y equals tan x, Draw a grid, again choose values 0 to 360 in steps of 30, and evaluate the tangent of x in each case. Now, they go 0, 0.58, 1.73, and the tangent of 90 is not defined. Then, minus 1.73, minus 0.58, 0, 0.58, 1.73, and the tangent of 270 is not defined. And then, minus 1.73, minus 0.58, 0. We can plot these points. And we can join those with a smooth curve. Rather than using a calculator and plotting the graphs, we can generate them from the original idea of points on a circle. Let's draw the graph of y equals sine x. If we draw a triangle inside a unit circle, then the height of the triangle is the sine of the angle. And so, the height of the triangle is the same as the height of the graph. As we scan across the graph, we draw the height of the graph to be the same as the height of the triangle. And this gives us our smooth wave curve. Now we can do the same thing again with the graph of y equals cos x. But this time it's best if we turn the circle on its side. So when we draw the triangle, the base of the triangle, which is the same as the cosine of x, is vertically up, in which case the height of the base of the triangle is equal to the height of the graph y equals cos x. So as we scan across the graph, we can draw the graph's height the same as the height of the base of the triangle. This gives us our smooth curve. To draw the graph of y equals tangent of x, we not only draw the circle, but we draw the tangent to the circle. As the angle increases, we have to extend the line of the angle in both directions until it meets the line of the tangent. Then the height of the tangent is tan x. So we scan across the graph, drawing the height of the graph the same as the height of the tangent. And this gives us the required curve. Now finally, in each of the trigonometry graphs we've seen that they repeat themselves, so if we draw an extended version, in this case going from about minus 180 up to 810 degrees, we can see for y equals sine of x, it repeats every 360 degrees. Similarly, for y equals the cosine of x, it again repeats every 360 degrees. But for y equals tangent of x, it repeats every 180 degrees. Now these graphs are important, and it's worth remembering them. To solve problems, you may often have to sketch them.